Okay, now let's look at the radar environment that's active. And what we've got are hostile airborne jamming aircraft, and they can have chaff too, and they want to jam airborne early warning aircraft from the carriers, and they want to jam them so these radars can't see these hostile aircraft that are going to try to attack these ships. And then we've got ground clutter there too. That's the environment that an electronic countermeasures environment is. You want to jam all these radars so that some hostile aircraft that might be near the jammer or far away, which we call a standoff jammer, so that they can't be seen, they'll get in close, be able to sink the ships. What do we do? Or cause damage to land assets. Well, this is the next thing, and it's what we call active masking. And active masking can be broken up into transmitting Gaussian noise, or what broadband barrage noise we call, over a very wide bandwidth. The bandwidth of, within C-band, it wouldn't be just the narrow frequency space within C-band that the radars could transmit in, but all over the whole radar band. We call that barrage jamming. But if you tune your jammer just to the frequency bandwidth of the radar, which is narrower than the whole frequency space available to it, that's called spot jamming. So there are two different forms of jamming, and we'll describe them later on. And then you can also mask the target by transmitting random pulses. And we're going to look at these things in terms of next. Now here are some U.S. radar jamming systems. The Air Force has an EF-111A Raven, which has up here transmitters and underneath. And these jammers generate noise-like signals in the radar's frequency band. And then a number of different types. Standoff, which I mentioned, or Escort, which are nearby. A jammer can be on the plane itself, which is the threat, which is self-screening. They'll point in the direction of the jammer, but you won't be able to get a range on it. And then there's spot versus barrage, which I went over. These deal with the bandwidth of the jammer, and these deal with the location of the jammer relative to threatening targets. Now, active masking, in that case, the receiver noise generally limits the sensitivity of most microwave radars. And we want to raise the noise level with a jammer to further degrade the sensitivity of the radar. And it will give out a big, at one angle, a strobe in the main lobe whenever the antenna points in the direction of the jammer. And it will give also in the side lobes, if the side lobes are high, it'll give massive false alarms. So when you have a jamming environment, you want really low side lobes. And spot jammers are jammers whose noise energy is concentrated within the receiver's bandwidth. Okay? So the ECM guy would, he'd listen with his receiver, find out what frequency the radar operates on, tune his jamming transmitter to that frequency, and then put all the energy he can into the receivers, that bandwidth he's transmitting in. Now, you can have frequency agility in the radar, can force the jammer to distribute the jamming energy over a wide bandwidth to go into the barrage mode. And a large number of radars in a geographic area may also force the jammer to, this is misspelled, to the barrage mode. Now, in the barrage jammer, the jammer radiates over wide bands of frequencies. Now, let's review the radar equation very quickly. It's basically, we've got the power density from an isotropic antenna, then it's the power density from a directive antenna, and here's the power density of the echo at the radar with the cross-section put in, and here's the power received by the radar, and it's got the aperture, the effective aperture of the receiving antenna, and that's what the received power is. Now, here's the target signal to noise ratio, and we did that all in the radar range equation lecture. Now, we need to calculate not the signal to noise ratio, but to the signal to interference plus noise ratio. So we have to add in, when we calculate the signal to total interference and noise ratio, we have to add in the jammer power at the radar. Now, the jammer's effective power density in watts per megahertz, and I'll give that the symbol delta sub J. It's in the receiver bandwidth of the radar. And the effective power density is that power density in the bandwidth times, you have to give it add the gain, directive gain of the jammer. And the jammer power that's received has added to it these other factors, which are the loss in the jammer, the received gain in the jammer's direction. Now that gain would be big if you were in the main beam of the radar, and it would be much lower if you were in the side lobes. Okay? And R sub J is the range from the radar to the jammer. So we have our radar equation is the same top part, but instead of on the bottom just having K, TS, BN up here, we have to add in these factors to calculate this ratio. Now what does it say? It says we want to have really low side lobes. That's a big thing. And what we want to do, if we can, is to force the jammer to go broadband, so that will force his power density per unit megahertz to be broad. We want him to have he's got a certain number of watts power density he can put out, and we want to have to force him to put it out over the whole spectrum that the radar could transmit at. And that's what this equation looks like. And in most cases, many cases, the noise power can be neglected because the jammer is really blasting away, and the signal to jammer ratio is just equal to this equation, and it assumes the bandwidth of the jamming pulse matches to that of the receiver pulse. That it's in blue because that's one you want to know. If you want to know if the jammer is going to bother you, you've got to plug these numbers in. It's just the radar equation, but it's with a jammer. It'll give you how strong the signal is relative to the jammer, and which is most likely to be noise. So then you'd plug that into your detection curves. Excuse me. Now for standoff jamming, to avoid producing a beacon-like emission from the target, which will say, he's out that way, go shoot him down. Lots of times they'll take a big aircraft and they'll put a lot of power in it, and it will be away from the hostile aircraft that will have munitions on it to sink ships and stuff like that, missiles. And they'll be from escort vehicles or standoff platforms, could be on the ground. The standoff jammers, they operate at a range which is usually beyond the range of the defensive system supported by the radar, and they'll orbit in safety. And one standoff jammer may cover a number of radars. And for a standoff jammer with within one beam width of the target, the temperature due to the jammer is often 50 to 60. That's 1,000,000 times greater than the temperature due to the receiver noise. So that tells you can really clobber the detection. Now, here is an airport surveillance radar that we've dealt with. And if we have the range from the radar to the jammer at 100 nautical miles, and the range from the radar to the target, they're supposed to see out to 60, and the jammer aircraft illuminates the main lobe, and this jammer has these characteristics where are not unreasonable. It's right on S-band. The losses in the jammer are this, and it's operating a kilowatt standoff per megahertz, the signal-to-noise ratio would be 14 dB, and the signal-to-jammer ratio minus 4 dB. So you're going to significantly degrade it and standoff in the main lobe. Now, if we look in the barrage mode, where you're further away and you have a lot higher power, and you have you're illuminating in the side lobes. The side lobes are down 23 dB, so the signal-to-noise ratio is 14 dB, and the signal-to-jammer ratio is 18. The signal-to-jammer ratio, which will include the noise, is 18 dB, which means that you're going to be able to see things okay. If you're in the side lobes, sort of, and you're a standoff jammer. Now, but we're looking in the side lobes, and the side lobes are down 23 dB. If you have a main lobe jammer that's a standoff, the signal-to-jammer ratio is low, and you won't see the target because your total signal-to-jammer plus noise ratio is minus 4 dB. So if a standoff jammer is jamming the main lobe, you're not going to be able to see aircraft at 60 knots. For example 1C, a standoff spot jammer that is side lobe jamming, and we've got ultra-low side lobes on the radar. The side lobes are down 55 dB from the main lobe, and the jammer illuminates the side lobes of the radar. And again, we've got the same standoff jammer. The signal-to-jammer ratio is 50 dB, so the ultra-low side lobes help us just amazing in making things work. And now in example 1D, we've got a barrage jammer in the side lobes, and here we've forced this guy to go broadband over from 20, not at 2800 or 28 to 3000, to go to the whole of S-band because the radar is hopping frequencies between every set of pulses. And the ERP is now down, if you've got the same total power, it's now down to 5 watts per megahertz. We see that the signal-to-jammer ratio is 41 dB, is 42 dB, so we're going to be able to deal with standoff barrage jamming quite easily. Now with escort screening jamming, that operates in a similar manner to standoff, but accompanies the penetrating raid and sometimes in the same range and cross-range positions. Calculations are the same as for standoff, increasing the radar energy in the direction of the jammer in the hopes of increasing the radar power so that the echo power is above the jamming noise. It's called the burn-through range. So if we could turn up the power on the radar, that we want to know at what range will we be able to see the jammer. Will it be above the signal-to-jammer ratio? And escort jammer is a tougher problem than standoff because the range is decreasing and becoming smaller. And the receiving jamming energy is increasing. And now for this example, what we've got is of the 100 watts per megahertz, and the escort jammers usually have less power than the standoff jammers. And we're illuminating in the main lobe. It's down near 0 dB. It's very hard to see in the main lobe. And escort barrage jamming in the main lobe. Again, if we force them to go with barrage jamming, the ERP drops way down, and the escort jammers usually, as I said before, have less power, and it allows us to see the targets because the jammer forced because the radar forced the jammer to put his energy over 200 megahertz instead of just a very narrow few megahertz, which is the bandwidth of the radar, 1.67. Now here's the self-screening range or crossover range equation, and that's when A small standoff jammer operating in the barrage mode can guarantee masking of the target echo. If you get in the main lobe and you get right next to the guy and you follow him right in, this is that self-screening range, and the jammer to signal power ratio at the input of the IF that's required to mask the radar signal is that much. And the jammer always has an advantage that you have to deal with by lots of tricks, which will, by putting nulls in the antenna pattern, which we're going to be going into, I think, a little bit later. Antenna power received at the radar. And because the jammer power varies with the inverse square of the distance between the radar and the radar varies with the fourth power. And that's why this is an R-squared dependence. And now for self-screening range equation. For this case, the self-screening range turned out to be 20 nautical miles when we used a spot jammer with 100 megahertz of ERP. And that's the jammer to signal power ratio at the output of the IF is required to be 10 dB. In that case, at 20 miles from the radar, you'd be able to see the target with this airport surveillance radar and these scenario parameters and these jammer parameters. Now we're going to move into deception.